Well, I don't know about you, but I think it's time we try to dig ourselves out of the anticlimactic note where we found ourselves at the end of the last lecture. So let's see what the benefits of cohomology are that homology does not enjoy. The main advantage is that because cochains are functions on chains rather than chains, it makes sense to take two cochains, no matter what their dimensions are, and multiply them. And it turns out that this has deep consequences for the theory of cohomology. Um, all of this makes sense on a very general level, but here I'm going to focus exclusively on the cohomology groups of simplicial complexes. So cochains are always to be thought of as living in a single simplicial complex. So let's make this precise. So K is a simplicial complex. This is part of our setup. And let's say we write the cochain complex of K as usual with the superscripts on the chains, on the cochain groups, and the superscripts on the co-boundary maps. And a little bit of notation that will really make life easy for us over the next few minutes is for every simplex, let's assume it's ordered. So there's a K simplex. We write for every I in 0K, the ith front face and the ith back face of sigma. So this is going to be sigma less than equal to I and sigma bigger than equal to I, and hopefully you can guess exactly what these are. So the first one is the I simplex that you get by only keeping the first I vertices. And this is why it's important for this to be an ordered simplex rather than an arbitrary one, because in an arbitrary one, there's no ordering of the vertices. And here, this is stranger. This is the K minus I simplex you get by keeping the ith vertex and everything from there onwards. So this is going to make life easy in terms of notation for us. These are just two faces of sigma obtained by partitioning the ordered list of vertices at I. So I and everything before, and then I and everything after. Okay, good. So here is the way we multiply cochains. And this is the main point of this chapter, and honestly, this is the main point of cohomology. If this did not exist, then I don't think cohomology would be all that interesting, or in any way, it wouldn't be so different from homology. Okay, so consider cochains. C, so this is going to be a k-dimensional cochain in the simplicial complex K. So let's write those K's clearly. So that K is the index, and then that's the simplicial complex. And eta is going to be some L-dimensional cochain in the same. Their cup product, which we will write as C cup eta. And in case you're wondering, that cup is not a union. So this cup is the latex symbol \smile. So it's sort of wider. So this is K plus L cochain. So it lives in C K plus L, defined as follows. So it's a cochain of dimension K plus L, which means it should eat up K plus L dimensional simplices and spit out numbers or elements of the field F. So let's go back to the top and say that this cochain complex is with coefficients in some field F. Okay, so here is how this cochain is defined. We need to define it on a K plus L chain, so it's enough to define it on a simplex and then appeal to linearity. So for every simplex Vk plus L, the cochain Xi cup eta sends sigma 2, and now we want to send it to a number. So what we're going to do is take the chain Xi, which is looking, it's a k-dimensional cochain, and so it needs a k-dimensional chain to eat. And so it's going to eat the first k things it sees. It is extremely hungry. And then you multiply it with, it leaves only the last L things for eta, and so eta consumes the last L things. And you should check that sigma greater than equal to k, so that's vertices vk plus 1 all the way up to vk plus L. That's going to be an L chain, or a basis L chain, and so eta sends that to some number in F. And this product, because Xi and eta both take values in F, is going to be something in F, and so as expected, this chain has eaten a k plus L dimensional simplex and produced a number, therefore it's a cochain. And linearity is enforced because we've only defined it on the basis and extended to all the chains by linearity. Okay, so we now have a recipe for taking two cochains. Remember, K and L don't have to be the same, so these are two cochains that live in completely different dimensions. And we've sort of smashed them together and produced a new cochain whose dimension is the sum of the original dimensions. There is no such recipe for chains. Chains are just vectors living in a vector space. They're not functions, so I cannot multiply them. But cochains, being functions, can be multiplied sort of pointwise. And that's what this cup product is doing. Okay, so now that we have a cochain, the question is, what is its coboundary? And that's addressed by a formula. Now, the proof is a bit of a slog, but it's extremely useful, so we will see at least a bit of it. So for Xi, a cochain, and eta, an L cochain, both of the simplicial complex K, here is the coboundary, and it has to be K plus L coboundary of their cup product. So take a breath, there are two pieces. So this is sort of like a Leibniz rule with a little bit of a twist. So so here we go. So the first thing we do is we take the coboundary of Xi and cup it with eta, plus -1 to the dimension of Xi, which was K. And the reason for this -1 will become clear shortly. And then you leave Xi alone and then take the coboundary in, of course, the correct dimension of eta. So that's the formula. I don't expect this formula to instantly bring any enlightenment to people seeing it for the first time, but it's important. So the consequences are importantly. So let's prove it. So let sigma vk plus L plus 1 be a k plus L plus 1 simplex. And why do I need a simplex of that dimension? Because when I take the coboundary of this k plus L chain, which is Xi cup eta, I produce a k plus L plus 1 cochain, and therefore it must act on simplices of this type. And we show that both sides of the desired thing that we want to prove, let's call it star, evaluate to the same number on sigma. So number in F on when you feed them sigma as input. And now the way to do this is to take the two pieces on the right-hand side and slowly, carefully feed them sigma one at a time. So I'm going to take this part and that part and have them act on sigma all at one at a time. So let's start with 1. This is the co-boundary of xi cup eta acting on sigma. So the two things that are being cupped here, the first one has dimension k plus 1 because it's the co-boundary of a k cochain, and the second one has dimension L. So this is going to be, by the definition of the cup product, this weird cochain to the co-boundary acting on sigma multiplied, sorry, not on all of sigma, on sigma less than equal to k plus 1 multiplied by eta acting on sigma bigger than k plus 1. Now, if you remember, this was the transpose of the boundary map, which we wrote, I think it would have to be the k plus first boundary map. That's just this bit is the transpose. So we know what it has to do to a cochain. It has to do the following. So you go from I equals 0 to k plus 1 of minus 1 to the I, xi acting on the simplex, but you remove the ith vertex from it. And this entire mess then gets multiplied with eta k plus 1. And because we want a certain cancellation to happen, I mean, the first time you do it, of course, you leave the eta outside in the privacy of your own home. But when you're doing it in public and you want to look like you know exactly what's going on, you should slide the eta into the sum. So because it's multiplying everything, you get I equals 0 to k plus 1 minus 1 to the I, xi acting on the first k plus 1 vertices except you remove the ith vertex multiplied with eta, and this second bit has no dependence whatsoever on I, so it doesn't matter whether we leave it inside or outside the sum. Okay, that was a bit of work. Take the second expression, and of course it's already scrolled off the screen, but it was minus 1 to the k multiplied by xi cup. And, well, you get something for it. And it turns out that the last, meaning I equals k plus 1 term of 1 cancels with the first term of 2. And this cancellation happens precisely because of the minus 1 to the k sign. That is attached to the second term. And okay, and when you do that, the remaining terms are the honest k plus L co-boundary of the cup product. So that's the basic idea. You take these two sides and sort of massage them into a form where they're almost what you want, but the last term of the first sum cancels the first term of the last sum, and then everything looks great. Okay, what's the point of this this formula? As a corollary to this cup product formula, so I'm going to omit the indices just to make life easier. This is that plus or minus xi cup co-boundary of eta. Okay, so you can make certain interesting conclusions out of this. The first one is that if xi and eta are both cocycles, that means both have trivial coboundary, then for instance, this stuff will be 0, and that stuff will be 0 by definition of a cocycle. Therefore, that entire sum will be 0, which means that this will also have a trivial coboundary and will therefore be a cocycle. So I'm going to summarize that entire calculation by cocycle cup cocycle equals cocycle. Similarly, if you had cocycle cup coboundary, this takes a little bit more work, but it's written in the note so you can check, gives you a coboundary. And in fact, if you flip these two, coboundary cup cocycle, again gives you a coboundary. Why are we doing this? Well, we're doing all of this because we want the cup product to be defined not just on cochains, but to be well defined on cohomology. And if you have these three things, you know that if you take two representatives of a cohomology class, you get sent to a representative of a cohomology class because all these things in the top row lie in the kernel of some coboundary map. Good, that's great. What if you perturb one of them by a coboundary? Well, if you perturb one of them by a coboundary, either the left one or the right one, then the difference between what you had before and what you have after the perturbation would end up being a coboundary by the second two formulas, which means that the cup product induces well-defined bilinear maps on cohomology groups. And it's sort of typical to use the same symbol for this induced map on cohomology by the cup product. So for any choice of K and any choice of L, so dimensions K and L, the map from the K cochains cross the L cochains to the K plus L cochains. That's a mouthful, but this map is just taking xi and eta and sending them to xi cup eta. This is well defined. I mean, you cannot, if you perturb cocycle within its cohomology class, or that one within its cohomology class, this one might differ by coboundary, but that's the worst thing that it can ever do, which means that it will be well defined as a cohomology generator. So that's great. What this means is that we're now suddenly in this universe where we can take cohomology classes, no matter what their dimensions are. So we can take two of them and multiply them together and produce a new cohomology class whose dimension is the sum of the dimensions of the two things that we multiplied. This is an algebraic structure that has a sort of well-defined name. Since we're working over a field, it has a terribly defined name. It's not well-defined. This is called an algebra over the field. So let me write this down. The direct sum, where you take all k bigger than 0 and just smash up all the cohomology groups, is a graded algebra. That's what it's called. Graded algebra over the field F. Now, I'm not going to write this down because we've done everything with field coefficients in this course, but if you sort of decided that you did not like fields and you wanted to compute cohomology everywhere with some ring coefficients, maybe a commutative ring, maybe the integers, then you wouldn't get what's called a graded algebra. You would get a graded ring. So you'd still have some sort of abelian group underneath, and then the product would happen not for a vector space, but for a module over that ring. So if that ring was integers, of course, you just end up with abelian groups. Okay, and the point is that even though in this direct sum that forms a graded algebra, if you knew the homology of K, then you'd know the dimensions of all of these vector spaces. So up to isomorphism, you'd know everything about this as a vector space. But the algebra structure, where you're allowed to multiply cohomology classes and get a new cohomology class, is completely opaque to homology. Homology cannot see it at all, whereas cohomology sees all of it. So there's a standard example of the phenomenon of cohomology algebras distinguish spaces with identical homology. So let me give you the standard example of this. So I think it's the simplest example of this phenomenon. So if you take K to be some triangulated space whose geometric realization is a torus. So this is, you imagine you have some triangulation here, which I'm of course not going to draw the whole way around. So it looks like S1 cross S1. Or if you want to be simplicial, it looks like the boundary of the hollow 2 simplex cross the boundary of the hollow 2 simplex. Okay, and if you let L be any simplicial complex that looks like a 2-sphere with 2 little circles attached to it. So this the official algebraic topology this is called a wedge product, and of course you can build this out of the hollow 2 simplex and 2 hollow 1 the hollow 3 simplex and 2 hollow 2 simplices. Sorry. Okay, so both have exactly the same homology, and so I'm not writing H, I, K, or L because it doesn't matter. They have the same homology groups. So over a field F, they're going to be one-dimensional for I in 0 or 2. They're going to be two-dimensional for 1 and then 0 otherwise. And the point is that, so as far as homology is concerned, and in fact, as far as cohomology is concerned, as vector spaces, these two K and L look exactly the same. But the point is that if you let Xi and Eta be the one-dimensional any one-dimensional cohomology generators. So it's a two-dimensional space in both cases. It's this F2, so you can find two linearly independent vectors there. So that's what I mean by generators. So they shouldn't be, linearly dependent on each other. Then the cup product is 0 in L, but non-zero in K. So, okay, you could do this computation by hand. You could triangulate the space on the left, you could triangulate the space on the right, and you could, everything I've said of this multiplication and all of that, you could check that one side gives you 0 and one side doesn't if you don't believe me, but you should believe me. On the other hand, there's a sort of beautiful geometric reason for the non-zero-ness here and the zero-ness here. And let's see if we can, there's my torus. So I said, let there be torus, and there was one here. So let's see what's happening here. This is a nice triangulated torus. And I want to show you sort of the pictures of what the one-dimensional cohomology generators look like. So there's going to be, let's just zoom in here for a second. There's going to be one that runs around what's called the equator. So it's a cochain, so it's going to look sort of jagged. Maybe something like that. And so it goes all the way around because the two simplices that show up have to cancel somehow. And then there's another one that goes around the other loop of the torus. So again, it has to be jagged. Let's see. Now at this point, I still want to go down, but I want to cancel this simplex. Okay, well, something like that will work. So this goes down and all the way around. And you see what happened here. There's going to be one of these two simplices, at least one two simplex, and there are two of them here. So each of whose faces are sent to something non-zero by one or the other so this can be Xi, that can be eta, and there exists a two simplex. So there's going to be some two simplex, which is highlighted in black here, so that Xi cup eta sends it to something non-zero in F. And the reason that two simplex is sent to something non-zero in F is because all of its faces are sent to something non-zero in F by either Xi or eta. And so what the cup product is doing is it's sort of measuring how these two cohomology generators are sort of locally product-like. There's no analog of this situation in the other example where you have here the cochain is going to live. This is going to be Xi and this is going to be eta, and there's no two simplex that has to be near them. They're sort of disconnected and they don't form a product in any nice way. So that's why it's non-zero in K and zero in L. So as hopefully you don't have to follow this calculation to the end, but the point is that the cup product is telling us things for cohomology that we had no hope of learning from homology alone. In our next lecture, we'll see an even stranger product that's available to both cohomology and homology. So I'll see you there.